Greetings everyone. Welcome back into another action-packed lesson from Calculus 2. We're going to continue our endeavor into power series by talking about other ways that we can create the link between a function that we would study and the power series that can represent it. Okay? So let's pick up where we left off in the last lecture. We were talking about representing functions with power series by using the geometric bridge, right? The geometric series comes from anything in a rational setup where I have my first term a over 1 minus p, usually 1 minus the r, and I can have some function there with x in it so that the x ends up being in the exponent of the geometric series, hence giving me some sort of power series in x, as long as your p of x is some polynomial in x. Okay, and that's why I use p of x there to demonstrate that. If it's going to be something else like a trig function or an exponential inside of that power, you're going to get something else that's not a power series. Okay, so it's important to remember we're going to be converting these rationals into something that has that polynomial in x. And here's a few examples like the ones that we finished up with last time. If I have 1 over 1 minus x, that's already ready to go for a certain format where x could be my r. So I'd have the sum of x to the n, right? This is my r to the n power is my geometric setup. And since it is geometric, my r, the absolute value of the r, has to be less than 1, which gives me an interval of convergence of x between -1 and 1, because the absolute value of x has to be less than 1. Okay? Or we could have chosen a different center. Notice the center of this series is 0 because it's x minus 0 basically. We could have chosen a different center, like say -3. I could have rearranged this fraction by adding and subtracting a few numbers and then dividing by 4, okay? Causing it to have this x plus 3 as part of the r of that fraction. So then the 1/4 x plus 3 becomes my r, and therefore that's what gets raised to the n power, times the 1/4 is where I'm getting the plus 1 on the 1/4 there. Okay? Now notice the r has to be absolute value less than 1, which means the absolute value of x plus 3 has to be less than 4, which means it's the interval of convergence is centered at -3 and has a radius of convergence of 4 now, right? So it goes from -7 to 1 in this case. Do you notice that both of these intervals of convergence stop at 1 though, on the right-hand side, the right-hand limit there? Notice I have an asymptote for this function at 1. So that's sort of poignant for you there. Also, you could have higher exponents in your r. If I have -3 over 1 plus x to the 4th, I could have written it as -3 over 1 minus negative x to the 4th, because I do need a subtraction in order to use this geometric formula. In which case the negative and the x to the 4th both get raised to the n power. I have an extra negative, that's where the plus 1 comes from, and then of course the 3 is also the first term. And I have x to the 4th to the n, so it's x to the 4n. And yet again my rate, the absolute value has to be less than 1. And of course that means my interval has to be between -1 and 1 here, because it's just the 4th root of 1, which is going to get me 1 for the radius of convergence there, centered around 0. Okay, so that's a little recap from last time. If it feels a little foggy, pause this, go back to that last one real quick, look at the last couple of things that we did. But then also I'm going to recap here as well. Okay? So here are some conversions that we need to do. Before we can start combining these things, we want to make sure we're converting between these two formats pretty solidly. Okay? So I've got a couple of rational functions that I want to convert into power series with particular centers in mind. And I've got a couple of power series that I want to convert back into rational functions using the geometric format. Okay, so this first guy right here, I want to have my center at -2. Well, right now I just have 2x being subtracted from the 1 there. So that's not going to work very well unless you want your center to be 0. right? Because there's nothing subtracted from the x. What I would really like to have, since my center is going to be -2, I'd really like to have x plus 2 there. Well, I know that there's going to be a subtraction of 2 on the outside of that because I can't take that away from the x. It still has to be -2x. But I want my center to be -2, so I have x plus 2. What does that mean? It means that -2 times 2, I need to put a -4 here to make this happen. But I can't just subtract 4 arbitrarily. I'm also going to have to add 4 in the same progression. So basically, I haven't changed the value. All I've done is subtracted 4 and added 4. Okay? And then my denominator is going to change into this now. So the next step in this is going to be 6 over 5 minus 2 times x plus 2. I can't use my geometric connection here unless there's a 1 with a minus. So to facilitate that, remember, all I'm going to do is divide by this to force it to be a 1. So if I divide by 5 in all 3 locations, my function then converts into 6/5 divided by 1 minus 2/5 times x plus 2. And in this case, now my r is here, right? That's going to be the r of my geometric series. So let's set it up. That means I've got the sum from n equals 0 to infinity. My first term, my a, is 6/5 times, I have 2x plus 2 over 5, all being raised to the n power. Okay, so I can sort of merge these together a little bit and play around with the numbers. This is an okay way to leave the series right here. That's not a bad way to leave it. Just so that you know, we can also consolidate some pieces here. Okay, let's start with the denominator. That's going to be 5 to the n plus 1, because I have 5 to the n, and then I've got another one to multiply in. I'm definitely going to have the power series part of this, which is the x to the power of n. In this case, x plus 2 raised to the n. And then I've also got 2 raised to the n here times 6. So I have 6 times 2 to the n. And there's a couple of things you could do with that too. I could take I could factor a 2 out of the 6 and add it into the 2 to the n power. That's one thing that you could do with it. That's pretty concise though. It's a good way to leave it. Okay, what about interval of convergence? Well, again, here's my r, right? So the absolute value of that guy has to be less than 1. But I can take the absolute value of the 2/5, right? That's just going to be 2/5. So I have 2/5 times the absolute value of x plus 2 is less than 1. Multiply the reciprocal. That's going to tell me that the absolute value of x plus 2 has got to be less than 5/2. So that right there is going to tell me my radius and center, and I can turn that into an interval of convergence, right? The center is, as requested, -2. And then my radius of convergence is now 5/2. So then my interval of convergence is going to be -2 minus 5/2, which is going to be 1/2, because 5 over 2, it's -4/2, right? Minus 5/2. Whoops, I made a mistake. I'm doing the wrong end first. It's -4/2 minus 5/2 is going to be -9/2. And then now do the other side. It'd be -4/2 plus 5/2, which will give me 1/2. Okay, so I have my interval of convergence for that one. Remember, what that means is I can pick any of those values to be x values. not ends, right? These are x is an element of that interval. I can pick x anywhere in that interval, and then it will cause this to be a convergent series. And not just any convergent series, it's going to converge to this function. Okay? So if I pick an x value anywhere in there, plug it into x, right? It converges, and it converges to whatever the x value would have been for this function. So one might say that that's a good way to approximate functions, right? You can plug in x values in an infinite series, add up just a few terms really quickly versus possibly doing a more complicated rational plug-in. Okay, a more complicated rational function here. I have g of x is equal to x squared minus 2x plus 1 over x plus 2, and we want the center to be 1. Now the center being 1 on this one is actually kind of nice. For one, I've got a lot of x's in the numerator here. I want to make sure that that's not in the way, okay? I can still have x's as part of this numerator piece as some sort of beginning term, but I have to make sure that I'm using the same center for my x's in all locations so that they'll easily combine once I get it into the summation form. Okay, so for this one, I'm going to start off by factoring the numerator and noticing that when I factor it, it comes out to be exactly the piece that I want for my center, right? I have an x minus 1 there waiting for me. In the denominator, instead of writing x plus 2, actually I'd like to write it the other way. I'm going to write it as 2 plus x. And I know that I want my center to be 1. So remember what that means is I would like this x right here to be something with an x minus 1 going on, right? I would really like to have an x minus 1 here. So to facilitate that, I'm going to do a minus 1, which means I'm also going to do a plus 1 to balance it out. And that's going to cause me to change up my denominator a little bit. I now have x minus 1 squared over 3 plus x minus 1. And I'm almost there. Remember, I want a 1 and a minus here. So I'm just going to divide by 3 in all of those locations. So dividing by 3 gives me x minus 1 squared over 3 over 1 minus negative x minus 1 over 3. Now make sure you're with me on that one, right? I divided by 3, so 3 over 3 is 1. Divide by 3, so it's over 3, right? Divide by 3, so it's over 3. And this plus right here became a negative negative. And remember, the reason for that is because I need a subtraction for this rule to work. Okay, so now where's my r, right? This chunk right here has got to be my r, right? That's the piece that I'm going to be using in the geometric conversion there as my p of x, the thing I've been calling the ratio, the rate of the geometric. Okay, so then this is equal to the sum, n equals 0 to infinity. My beginning term, I have x minus 1 squared over 3 times all of this to the n power. So that's negative x minus 1 over 3 to the n power. Now we can clean that up a good bit. Let's do that. So I have the sum, n equals 0 to infinity. I've got x minus 1 to the n, and then I've got 2 more of them here. I've also got 3 to the n, and notice this negative. Think of it like a negative 1 to the n. Let's start with that. I have negative 1 to the n. And in the denominator, I've got 3 to the n because of this, and then I've got 1 more, so plus 1. Because I'm going to be multiplying those, so you add the powers, right? Times x minus 1 to the n, right? That's this. And then I've got 2 extra, so plus 2. And then I've got my series that's centered at 1. You see, what I was saying before about making sure that all of your x's have the x minus 1, the similarity, so that I have something nice to combine later on. Makes it easier to simplify that piece. Okay, so now let's do our interval of convergence. Remember, we want our rate here to be absolute value less than 1. So this piece right here is telling me that the absolute value of x minus 1 over 3 has to be less than 1. And that tells me, if I multiply by 3, that the absolute value of x minus 1 has to be less than 3. Okay, now remember, that's our center and our radius of convergence, right? So that center of 1, as requested, and then the radius of convergence then is 3. So here's my infinite series, my power series, and it has an interval of convergence that starts at centered 1 minus 3, so negative 2, and then centered at 1 plus 3, which would be 4. Okay? Now you'll notice on all of these, I've left all of the endpoints and the intervals of convergence as parentheses. And remember, the reason why I'm doing this is because these are geometric connections. And geometric series diverge at the equal to on the ones of the rate. Okay? If I were using some other test, ratio, root, something like that, then I would want to go ahead and start testing these endpoints. Okay? But these are straightforward, just connections with geometric series. Okay, what about the reverse? Right? If I start with a power series, can I take something that's just a simple power and convert it back into a rational function? The answer is yes. Okay? But remember, it needs to be something that's just a simple x to a power and just numbers to a power, things like that, maybe with a few extra pieces. Okay? We can't have just a multiplied n or a multiplied n plus 1 or a divided n plus 1 or n factorials. If it's got any of those in it, those are some of the more advanced ones that we're going to get to in a few lectures. Okay? But for something that's basic, it just says x to the n, and it just has a few other things maybe to the n, and then just maybe some numbers or some extra x's, whatever. Then we can convert that with this format. First, I'm going to start by rewriting this. I'm going to pick out the extra pieces because I want one rate, one r to an n power. I need one object to an n power. I need something that does this. And then this, I can use some entry piece over here. So I'm noticing that I have an extra 8 with that plus 1 there and nothing else. So that means I have a 1 over 8 out here because that's the extra 8. And then I have 3x and 8 all to the n power. So this is 3x over 8. So now I can see what my a and my r, or in other words, my p of x, right? So then this is going to be equal to 1/8 over 1 minus 3x over 8. And I'm just going to multiply by 8 in all of the locations. If I multiply times 8 times 8 times 8, then that's going to give me 1 over 8 minus 3x. And voila. We have our function that this is equivalent to, right? The interval of convergence here, by the way, 3x over 8 has to be less than 1. So that means that x has to be between negative 8/3 and positive 8/3. Right? My center is 0. Now, a little bit less common is whenever you will have your powers of x in a denominator like this. In other words, we might be dealing with some of those negative exponents is what it looks like. This is not as common and something that you may run into in a more advanced situation. Okay? I did notice it in a few of the homework problems that some of my students had, so I wanted to go ahead and throw this out as an example. The idea here doesn't work any differently, though, than what we've been doing. However, we won't be seeing too much of this because it sort of defeats the purpose of what we're doing. The purpose of what we're really doing here is trying to write these with positive powers to make this sort of thing easy as an approximation to something that's more complicated to do by hand. However, this is an important tool in the larger spectrum of things. So let's talk about it. Again, I'm going to look for the extra, and I'm going to write everything in a more concise manner. So I have my sum. I've got my 3, right? That's this piece. And I'm noticing the plus 1, right? So the plus 1 there, I'm going to have like this, x plus 5. So it's x plus 5 to the 1, but it's in the denominator, you see, right? Times, and then I've got 1 over x plus 5 to the 2n. Okay, so I need one object. Remember, I need one object to the n. 1 is the same thing as 1 to the n, right? And then this is to the 2n, but that's okay. I can just separate the exponents. What I'm going to do is write this as 0 to infinity, 3 over x plus 5 times 1 over x plus 5 squared all to the n, like so. Okay? So now, from this aspect right here, I'm going to say that this is equal to my a, which is 3 over x plus 5, divided by 1 minus 1 over x plus 5 quantity squared, like so. And you can sort of clean this up a little bit by multiplying everything by the x plus 5 quantity squared. Multiply that here, here, and here. Okay? So that's going to give me 3 times x plus 5. And remember that that's because what I'm doing is I'm multiplying x plus 5 squared. So if I multiply x plus 5 squared, right, one of these and one of these is going to reduce. And then I'm going to do the same thing here, x plus 5 squared, and same thing here, x plus 5 squared. Okay, so that's going to result in, here I'll have x plus 5 squared, because it's times 1, minus 1. So then, to make it look like just a normal rational function, that would be 3x plus 15 over, here if I FOIL this out, I'll have x squared plus 10x plus 25 minus 1, so plus 24 would be my rational function. Okay? So I can convert anything that's a simple power series, and I say simple by, just x to the power and no other floating n's or factorials or anything more complicated than that. We can convert those back into rational functions using the geometric format that we've learned at the very beginning. Okay? So this is the basic idea of converting them. Next, what we need to talk about is the actual ways that we combine multiple of them, and that can be actually useful in making more complicated functions into power series. So the first combining method, probably the more common one as well, is when we have 2 or more series that we can add together. And this sort of goes along with the series really well because they're already made of addition. But basically the theory, and feel free to look this up in the OpenStax book or whatever the textbook you have. If you have a series that converges to F and another series that converges to G, adding the 2 infinite series together will converge to F plus G, Subtracting them would converge to f minus g, whatever way you want to look at it, as long as they share a common interval of convergence. If one of them converges over here and the other converges over here, then there's simply no way to add them because you're not talking about the same x values. But if they overlap their intervals of convergence, then whatever the piece of the interval that they share, that is the interval of convergence of the sum or difference of the two series. Okay? Now, how does this work to my advantage in a single function? I'm not adding two functions. True. But let's say I have a function like this that has a more complicated denominator than I would like to deal with. And I know what you're thinking. In the last section, we just completed the square, which that works fine too, but that sort of closes you in on a center. For this one, I want you to notice that I can break it up into two simpler denominators, and then we're going to use partial fractions to make this into two smaller fractions, in which case the series will be much easier to see. So look, that's how we'll start. This piece right here is going to be equal to 7 over x plus 3 times x minus 4. If I factor the denominator, you can see x plus 3, x minus 4. And as you're hopefully familiar at this point, I can factor this into something over x plus 3 plus something over x minus 4. And then we go through our method of partial fractions to determine what the a and the b are. Well, in this case, the a and b both come out to be 1, but one of them is negative and one of them is positive. In this case right here, this is a negative 1 and this one is a positive 1. Okay? If you're not familiar with the partial fractions, please pause and go back to the last unit when we were talking about that with integrals. Partial fractions is a very useful tool in lots of situations that deal with fractions. Okay? So I used partial fraction decomposition to get to here. Now notice once I'm here, I have two very simple, straightforward, rational functions that I just need to manipulate a little bit in order to get them to the point where they can merge here. Okay? So what I'm going to do is I'm going to use the center of 0, right? So that I don't have to do a lot of manipulation, and you can see how these two come together. I'm going to take these two and I'm going to just rearrange them. So for this, I've got negative 1 over 3 plus x. Okay? However, I don't want the 3 here. I'd rather have a 1. So I'm going to divide by 3. Divide by 3, divide by 3, divide by 3 in order to get the 1 that I need right there. Okay? And then, of course, this plus, I'm going to use a double negative by saying minus negative x over 3 like that. So this first fraction I just manipulated by dividing and switching a sign. Plus 1 over x minus 4. I'm going to change the sign on those. Negative 1 over 4 minus x. Because I really wanted to have the subtraction on my x. And then again, I'm going to divide by the number it takes to give me a 1 here. So I'm dividing by 4. And then 4 over 4 is, of course, the 1 that I needed. So I have this. So now I have two things ready in the geometric format there. Okay? So let's set them up. I have the sum, n equals 0 to infinity, of negative 1/3 times negative x over 3 to the n, plus the sum, and you can use the same letter here for n, that's fine, because I'm just going into a different series. Technically they're different n's, but that helps me keep everything lined up, and actually I'm going to merge them, because remember, summing right here with the sigma just means adding anyway, And so does this. This is adding. So I'm going to merge these together eventually. Times negative 1/4, because that's my a value here, right? And then my r is just the x over 4. X over 4 to the n. Okay, so now let's merge this together. I'm trying to get one power series that represents the original function. And remember the theorem that I threw out at you. If I have two different power series that converge each to different functions, right? So this would be the little f and the little g function. And when I add them together, I get the total function. This series converges to that. This series converges to that. I can add these together to converge to the original total as long as they share an interval of convergence. Okay, let's go ahead and finish simplifying this, and then we'll find that interval of convergence. So I'm going to rearrange the terms here, and I'm going to get one big sigma going now. Since this is addition right here, I'm just going to merge these together with one single sigma right here. My first one has a negative 1 to the n, and then I've got an extra. So I've got negative 1 to the n plus 1 there. Okay? And then I've also got 3 to the n plus 1. Like so. Plus, yeah, I know. I hope you noticed I skipped, all right? I didn't do the x to the n yet, right? Watch. I've got a negative 1 over 4 to the n plus 1. Okay, I'm going to close this bracket, and then I'm going to put x to the n. And there's my series. That's my power series representation for this function. All I did was I had x to the n in both of them. I factored it out. This sum and this sum get merged because all I'm doing is adding a bunch of additions, right? Bunch of additions, more addition. It all just comes together. And then I just use a little bit of factoring. Now, you could pull out a few more things here, like you can try to pull a negative out front or something like that, but really this is a good, concise way to leave this particular series. Okay, now what about the interval of convergence? Well, I have two different series that I merged into one series. So I have to look at where their intervals overlap, if they overlap. Okay? So the r in the first one tells me that the absolute value of x over 3 has to be less than 1. And from the other one tells me the absolute value of x over 4 has to be less than 1. Okay, so then this one's telling me absolute value of x is less than 3 if I multiply by 3. This one's telling me absolute value of x has to be less than 4 because I'm multiplied by 4 on both sides. This is going to give me an interval that's between negative 3 and 3. This is going to give me an interval that's between negative 4 and 4. Okay? So if you look at these two together on the x-axis, right? So if I have my x-axis here, here's negative 3, here's negative 4, here's positive 3, here's positive 4. From negative 3 to 3 is in here. This is negative 3 to 3. And then negative 4 to 4 is out here. I can only have an interval of convergence where they overlap, where they share. They have a common interval of convergence. So that's going to be here, right? From negative 3 to 3. They both have the negative 3 to 3 because that fits inside of negative 4 to 4. Okay? So overall, the interval of convergence for this series is whenever x is a member of negative 3 to 3 interval. Okay? So here's my series, right? And then that's my interval of convergence. All right, let's try again. Right here, I've got a fraction, and I notice that the denominator is already factored. So I'm going to try and use partial fractions to separate that out. right? So I've got the negative 10 over x squared plus 9 times x squared minus 1, and that's going to be equal to ax plus b over x squared plus 9 plus cx plus d over x squared minus 1. Now wait a minute, Professor Simon. That x squared minus 1 can be factored and brought down lower. You're absolutely right, it can. But I'm not going to do it because I want my x's to match when I get into the series. It's the same idea as what we were talking about earlier. If I'm combining these multiple pieces in series, I want them to have these common pieces. Like right here, these both had x to the n. I want to be able to factor that out so I can turn it into one power series where I have one single type of x raised to a power of n. Okay, so I can factor this further and I can break it partial fractions further, but I'm not going to do it because I want them to match. Okay, so in this case, as it turns out, the a and the c end up being 0, and the b and the d are also both going to be 1. One of them's negative and one of them's positive. So this one is the negative. Oh, no, it's the positive one. And this one's the negative. And the way I'm able to tell, guys, is I just multiply right here. X squared minus 1 and negative x squared minus 9 will give me a negative 10 total. Okay, so this one's pretty easy to check. But go through your partial fractions. Make sure you're in agreement with what I'm getting here for this one, okay? Now, I have both of these in singular looking fractions, just like I did before. So we just need to manipulate them to look like what I need for a power series. Okay, so I have 1 over, I'm going to do the 9 minus negative x squared, right, for this to work. And then on the other guy, I'm going to have the negative 1 over. I'm actually going to change the signs on this so that I can do 1 minus x squared here, right? If I want to flip this around, it changes the sign on everything. I need a 1 here, though. So I'm going to divide by 9, right? That's going to make this a 1. I'm going to divide by 9, divide by 9. This one already had the 1 and the subtraction here, so he's ready to go. Okay, so here we go. This is going to be equal to the sum n equals 0 to infinity. I've got a 1/9 a value, and then my r is the negative x squared over 9. So negative x squared over 9 to the n plus, and then for this other guy, I've got 0 to infinity. Just the x squared is my r, my a is 1, right? So I've just got x squared to the n there. Okay? So let's consolidate these a little bit now into one power series. I'm going to have one big sigma, 0 to infinity. I've got a negative 1 to the n power. Okay, so here's my bracket. I've got negative 1 to the n. In my denominator, I have 9 to the n plus 1 more. So 9 to the n plus 1. Plus, there's nothing extra over here. It's just 1 plus 1. Like that. Okay? And then both of these have x squared to the n. X squared to the n. So that's just times x to the 2n. Okay? Now, of course, you can, go around about and start simplifying these things. You could do 9 to the n plus 1, top and bottom, and just, go crazy with that if you really want to. You don't need to. I mean, it's not going to change very much, what it already is. Okay? Now, interval of convergence, right? Let's talk about the interval of convergence here. I have my two series that I need to look at the rate, right? For this guy right here, the absolute value of x squared over 9 has to be less than 1, which tells me absolute value of x squared has to be less than 9. Of course, with x squared, you don't really need the absolute value, but so when I take the square root, I get that split, right? I get that x, when I take the square root, is going to be between -3 and 3. And then for the other guy over here, I've just got absolute value x squared has got to be less than 1, right? That's my r. Okay, so then I get that x has got to be somewhere between -1 and 1. And remember, the only way this is going to converge is if these two intervals of convergence overlap. And as you can see, this one is going to fit inside of that one. So my interval of convergence is the one where they meet, the one that they share in common. The common interval of convergence here is from -1 to 1. So I've got a power series, right? And then it's got that interval of convergence. Okay, next one. This one's slightly different because it has a variable in the numerator. But just like one that I did earlier, I'm going to sort of take that x squared and sort of just pull it outside. Okay? I'm going to rewrite this function as just x squared times, I'm going to have 12 in the numerator, like this. And I'm going to factor out this denominator. That's going to give me 4 minus x times 2 minus x. Okay? Now I know what you're thinking. I would have factored that with the x squared in front and did, x minus 4, x minus 2. And you'd be perfectly well within your rights to do that. However, I'm taking advantage of the fact that I know that I'm going to want something minus an x, right, in my fractions. So I left the 8 in front and the x squared in back so that I could have both of these reversed. It factors the same either way, but with this way, the double negative pushes the negatives on the x. So therefore, these two are already set up and ready to go into the format that I need. Okay, so real briefly, I need to take this, right, 4 minus x, 2 minus x, and I need to split this into something over 4 minus x plus something over 2 minus x, like so. Okay? So again, if I notice that if I have a 2 minus x times a and a 4 minus x times b, and then I'm going to, of course, do the plugins there, where I'll have where x is 4 and where x is 2. I'll show you real quick. Right? I know we haven't been going through all of these steps, but this one's not as straightforward as the other ones. Okay, so if I let x be 2, notice that I'm getting 2b equals 12, right? So b would have to be 6. And if I plug in 4, this zeroes out. 2 minus 4 is -2, right? A would have to be -6. Okay. So in my partial fractions world here, that means I've got a -6 here and a +6 here. Like so. Okay? And of course you can always double check that, right? You can bring it up here and you'll have 6x and you'll have your -6x there. The x's will go away. You'll have the -12 and the +24 will give you +12. So it matches out. So now I want to take both of these guys, and don't forget, we actually have an x squared times this whole thing, right? So I've got x squared now. I'm coming back to my original plan here. I've got x squared times, I'm going to arrange this guy so that I can rewrite him in a power series, right? Now, I don't want to change the center, right? If I change the center away from 0, then this piece right here, the x squared, is going to be off center, right? Because I don't have x minus or plus anything here. I'm going to keep these things centered at 0. Okay, I don't want to shift it away from that without doing something else more complicated with that x squared. So from here then, I'm going to divide everything by 4. That's going to give me negative 3 over 2 over 1 minus x over 4. Plus, I'm going to divide everything by 2 here. That's going to be 3 over 1 minus x over 2. Okay? Now, from here, I'm going to make those two series. So I have x squared times the sum from n equals 0 to infinity. I've got the negative 3 over 2 times x over 4 raised to the n power, plus the sum from n equals 0 to infinity. For this guy right here, that's just going to be 3 times x over 2 raised to the n power. And I close the big parentheses for the x squared there. Okay, so now what I have is x squared times the big sum that I'm going to merge both of these into. Big old bracket here, right? Okay, so from here, I can think of this 4 like a 2 squared. Okay, now let's think about why I'm doing that for a second. Because I want to be able to consolidate this as much as possible, right? I'm going to think of this 4 right here as a 2 squared. Because this is a 2 right here, and notice this is also going to agree. It's going to be a 2 right there. So what I have is 2 squared to the n. So that's 2 to the 2n. And then I've got an extra one over here, which will give me a plus 1 on that. Right? So I've got 2 to the 2n plus 1 there, like so. I also have a negative and a 3, and that's it for that one. It's not to the n. Plus, I've got the 3 on this one, which is just there. And then I have 2 to the n, like so. Okay, and then I have x to the n, x to the n. So it's just going to be x to the n. Okay? All right, so now let's go ahead and finish consolidating all of this. Sum n equals 0 to infinity. Looks like I can factor a 3 out of both of those. That'll make it easier. 3 times, and then I've got negative 1 over 2 to the 2n plus 1 plus 1 over 2 to the n. You know what? We can actually... No, we can't. Let's leave it alone. Because that's 2 to the 2n, that's 2 to the n. That's not going to work out good for us. Just leave it just like that. This is 2 to the 2n plus 1 and 2 to the n. And then I've got x to the n, right? And then there was an extra couple of x's right here. I'm now multiplying those in. So I'm going to add the exponents, n plus 2. Okay? So what about the interval of convergence? Well, that's going to be very similar to the stuff we've been doing, right? You can see that the first one has an interval of convergence where x over 4 has to be less than 1, right? So absolute value of x has to be less than 4, which means x has to be between 4 and negative 4. And for this guy right here, x over 2 has to be less than 1. So of course that's going to lead me to x being between 2 and negative 2. And I need to pick the interval of convergence that they have in common, right? So here's my power series, and I've got an interval of convergence of x being an element of negative 2 to 2. Okay, with that as my power series. Okay, so hopefully you see where I'm coming from with this, where we can actually take two lesser, smaller, well-known, easy power series structures and bring them back together into one power series that can represent the original function. Okay, and you don't have to do this with just two, although very commonly it is two. If I had multiple, like 3 or 4 or 5 of them, you could do the same thing. And then you just have to find the interval of convergence where they all meet up. Okay? But this is a very solid tool for being able to convert rational functions that have multiple parts into a single power series. Of course, if you can do the addition of power series and they will equal out to the total sum of what they converge to, then you can also do the same thing with multiplication. If you have 2 or more series that both converge to to each of their own functions, right? So if I have function a that converges to some a of x, and I have function series b that converges to some function b of x, then if I multiply series a times series b, then you will get that product will converge to a of x times b of x, as long as they're on that common interval of convergence. So you have to have still that common interval of convergence. You can't just pick whatever intervals you want, because both series have to converge, right? So they have to be an overlapping interval of convergence. However, it's not as straightforward as the other one. You can't just multiply each of the corresponding terms. As you know, whenever you multiply strings of added, powers of x, you have what in your olden days you would have called FOIL, but in a more grander scheme, it's more like just multiply everything by everything in some sort of convolution of big groups times other big groups. So a lot of times with this particular method, we end up doing a lot of little multiplications in search of some sort of pattern. And if we can't find a pattern, then we just suffice it to where we go out, 5 or 10 terms and just say, okay, I'm going to use this small power series. And it just depends on how much accuracy you need, right? And we have methods of determining what kind of accuracy we need as well. Saying we want so many decimals of accuracy, so then I need a power series that has so many terms in it, so on and so on. But what you start with is constructing the power series. Because of all the little small multiplications that come into it, very often you don't have just one big thing, like with the addition that we just did, where I can just pull it out into one nice pretty formula. Okay, so here's an example, and I'm going to show you by filling up this board with a lot of multiplications. Okay, so the first thing that we need to notice is that we can factor the denominator here into 21 over x cubed minus 1 times x squared plus 1. Right, and of course you can do that by grouping. And yes, I know you can factor this one out even further, but I really don't want to complicate things for us by making more than one thing, because the more objects that we have is the more really small multiplications we'll have to do. So I'm just going to split it into these two, since I can get them into binomials, right? That's really the main thing here. I was able to get each of these into some sort of binomial format, and that really works out really well. Okay, I'm going to go one more step, and I'm going to make this negative 21 over 1 minus x cubed, and 1 plus x squared doesn't need an extra sign to reverse. You'll notice what I did was I reversed the subtraction, which is where the negative on the 21 comes from, and I reversed the addition. And remember, the reason is so that I can have those as easy little pieces to do. I am then going to rewrite this as negative 21 times 1 over 1 minus x cubed times 1 over 1 plus x squared. Okay? So then I'm going to convert both of those rational pieces into their infinite series counterparts using the geometric format. Okay, so then this is going to be equal to negative 21 times the sum from n equals 0 to infinity of, now notice here my r is just x cubed, so I will have x to the 3n, and that's it, times the sum n equals 0 to infinity of, here I'm going to need to employ the double negative, right? I'm going to have to make this minus negative x squared, I mean. So I'm going to have negative 1 to the n, x to the 2n for that one. Okay? So now I've got my two series, and real quick, just on the side, let's get their intervals of convergence. Notice for this one, I have to have x to the third absolute value is less than 1, which tells me that my interval is between negative 1 and 1. And again, over here, I'll have x squared has to be less than 1, which has the same result. Since they have the same interval of convergence, there's no argument as to where they overlap. Their interval of convergence is going to be from negative 1 to 1 here. Okay, so that's my interval of convergence. So the best way to do this now is I'm going to write out a few terms of each of those power series, and then I'm going to start multiplying. So then this is equal to negative 21 times. The first series there I have, when n is 0, right, I've got 1 plus x to the 3 plus x to the 6 plus x to the 9 plus x to the 12, so on and so on. Right? It goes up by 3 every time. 1 times 3, 2 times 3, 3 times 3, 4 times 3. And the next one is just an alternating, and the power goes up by 2 every time. So I'll have 1, right? When n is 0, negative 1 to the 0 is 1, so I've just got positive 1. But then it alternates, so minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th, and so on and so on. Okay, so now what I propose is to set up a chart of multiplications for you, or we can, not necessarily a chart, but a grouping list so that you can see where I'm going with this, right? Because what I'm going to do is I'm going to be doing multiplications here, right? I'm going to be doing all of this times 1, and then all of this times negative x squared, and then all of this times x to the 4th, because that's how our multiplications go with these polynomials. You've got a lot of little pieces to worry about here, okay? And then of course at the end I'll have the negative 21 multiplied into it. So for right now I'm just going to focus on the polynomial pieces here. Okay, so my first bit out, I'm going to have just the 1 plus x to the 3 plus x to the 6, 9, 12, so on and so on out, right? And then I'm going to have that same thing times negative x squared and then again times x to the 4th negative x to the 6th and I'll do one more, x to the 8th, right? 3, 6, 9, 12, so on and so on. Okay, so these are all the multiplications that I'm going to be doing, and of course this goes on, forever this direction also as it does this direction. Okay, so here's what I wanted to show you by making a chart out of this, as I was saying. I'm going to consolidate all of this information into a chart here. Okay, so I'm going to say that it's going to be the exponents in this direction. So it'll be x to the 0, which is 1, right? X to the 1, 2, 3, 4, 5, 6. These are all the exponents of x. Okay? And basically, this is just a good way to keep me organized. 7, 8, 9, 10. Let's go out to at least 12. Okay? So, on each of these lines, I'm going to put a multiplication, right? So this first line right here will be this multiplication. Okay? So I have 1x to the 0, I have an x to the 3, I have an x to the 6, I have an x to the 9, I have an x to the 12. Okay? And it of course would keep going if we wanted to keep doing our pattern. Then in this next one, notice I have x squared times 1, right? So for this next multiplication here, that's this line, I'll have a negative 1 for the x squared column. That's the first multiplication. Then it'll be to the 5th. So here, and it's going up by 3 every time. Notice the pattern, right? Because these are going up by 3 every time. So again, I'll just be able to go up by 3s. 3, 1, 2, 3, right? And then 1, 2, and then of course it would be over here. Okay, let's keep going. The next line will be this multiplication right here. So I'll start with x to the 4 times 1, that's here. And then 7, 10, it's going to go up by 3 every time. 7, 10, so on. Hopefully that you're seeing the pattern that's going on here. I'm starting at a staggered amount because of the way these multiply, but then once I have my starting point, you see they just go up by 3s every time. So what I'm doing is I'm building a pattern here to help me create this polynomial. Okay, so then this next one is going to be this multiplication here. I'm going to start with a negative 1x to the 6th, so that's here. And then it's going to go up by 3 every time, so 1, 2, 3, 1, 2, 3, right? It would be here at the 12, right? Because that'll be that one. And then it would keep going from there. And then, let's see, I'll squeeze in this one more, and let's see if we can get the pattern from going from here. I'll start at x to the 8, right, with one of those here, and then it's going to go up by 3 every time. So 1, 2, 3, right, and then so on and so on. Let me do one more, right? So the next one would be x to the 10th times all of that same stuff, right? So I would start with a negative, right? It's negative x to the 10th. And then it's going to keep going forever that way. Negative x to the 10 this is going to be this line here. So that's negative x to the 10, and it's going to go 1, 2, and then it'll be from there, right? It'll keep adding in the 13 column. Okay. All right. This is actually far enough for you to see the pattern. Okay. I know it may not seem like it just yet, but watch this. Get some of this out of the way right here. Okay. So look at what happened here. I have x to the 0, I have one of them, okay? That's going to give me 1. I have no x to the 1s, okay? So no x's. I have 1 minus x squared there, okay? I then also have from this column plus x to the third and plus x to the fourth, right? That's this column. I then also have minus x to the fifth from this column here, right? That's this one. There, the x to the sixth is gone. There is an x to the seventh, so plus x to the 7. Okay, now notice 8, 9, 10, 11, and 12 of what I have all wipe out. So I have up to this far, and then everything over here has zeroed. But wait a second. The very next multiplication would be x to the 12, okay, times all of the stuff. Which means right underneath here there would be a rebirth, okay, with the x to the 12. There would be another right here. So the very next term would be x to the 12th. But what you need to see is that since these all wiped out in a big large group, and then it's like I'm starting over up at the top with a new group, but with x to the 12. Okay? Everything after that is going to be like this grouping here, and it'll do this many terms and then wipe out a bunch, and then it'll be x to the 24th. Okay? So that's actually the pattern for this one. You have this starting amount, and then all of the groups add up the way they do. And then you have this big cancellation, and then it starts again after another 12 exponents, right? So it goes in these groups of powers of x to the 12th. Okay, so I have this polynomial right here. And by the way, if you just do this polynomial, 1 minus x squared plus x to the third plus x to the fourth minus x to the fifth plus x to the seventh times negative 21, that alone mimics this function extremely well on the interval negative 1 to 1. And I'll show you the graph of that in just a second in GeoGebra. Okay, but let's go ahead and officially write this out. My sum, I've got n equals 0 to infinity here, negative 21 times 1 minus x squared plus x to the third plus x to the fourth minus x to the fifth plus x to the seventh. And then this is going to be times x to the 12n. Okay? Because it goes in those groups every 12 exponents. And then it has the same grouping every time the way these things add up. Because I can just factor the x's out in the groups of the 12 afterward. Okay? It's just the way this one follows. Sometimes the problems may ask you only to give the first few terms, right? So in which case you would say negative 21 and then maybe give 4 of these terms or so. It just depends on what your requirement is. This particular one, we were lucky. We actually found a pattern, and this pattern does actually work out as a very nice approximation for that function on this interval only. Okay? As you can see, this is a very involved process though. So this is not one of the things that we just jump right out and say, let's go for multiplication right out the bat, right? It's not something that we tend to do as a first choice, because it is a lot of work and a lot of preparation to make sure that everything lines up right, a lot of little multiplications. But it is a method that you do need to know exists. You do need to be able to multiply them and find the common interval of convergence. And you do need to know how to keep your stuff organized and make sure that you get a good function approximation. Okay? Okay, so here's that function that we were just talking about, and as you can see, I have a very specific scale set up. It does actually take some large negative y values before you see the interesting side of this particular function. If you were to put it on a normal scale, you probably wouldn't even really notice it, you see, when you start getting low values. So I shrink it so that we can get the interesting features of the function here. And we're really focusing, I spread out the x-axis a good bit for us, because we're really just focusing between negative 1 and 1. That was our interval of convergence for this. So here's our basic summation right here that we said. The 1 minus x squared plus x cubed plus x to the fourth minus x to the fifth plus x to the seventh, and then it'll be times x to the 12 times n, and I'm gonna have this slider to do different sums of n to varying sizes. Okay, so for starters, I just have 0. So in other words, just those first few terms. So take a look at the graph over here. As you can see, just those first few terms, not even going past x to the 7th, already approximates very, very decently this middle curved section. And it does deviate a good bit here, but as soon as I go up n equals 1, you see I've got the next set of terms times x to the 12th. It's already starting to approximate this thing very, very closely. And I can go another couple of steps here. So as you can see, this has already gotten to be quite a big approximation, and it does actually squeeze in really nicely into this function. And it's just between -1 and 1 here. So let's go ahead and maximize this thing out. You can see after you get far up enough, it doesn't really make as much of a difference. It just starts closing this gap over here. But it's an awesome approximation, even at a low value, when you just go up this high right here, to most of the values in there. And even when you get close, it doesn't deviate that much. It's a very good approximator. So I hope this has helped you understand the ways that we can add and multiply power series in order to get other representations for rational functions.